Hello, everyone, and welcome to this free webinar presented by WePast. My name is Cristina Ruiz, and I will be your moderator today. Throughout the webinar, we will stop the presentation to review. There will be multiple choice review questions which you will be able to answer in the polls section. Please go ahead and respond to these questions as they come up. You will have about a minute to answer each one. During the webinar, please feel free to use the chat to ask questions and discuss the topic. We will take time after the presentation to answer these. This and other recorded webinars will be available to WePast subscribers. You can register through wepast.com to become a subscriber. Today's topic is the Basic Physics of MRI, presented by Dr. Jeffrey Clark, Professor of Radiology at the University of Texas Health Science Center in San Antonio. Thanks for joining us, Jeff.
Glad to be here. So today we're going to just discuss some of the basic physics of MRI. As you know, MRI is becoming an increasingly important imaging modality in radiation oncology, and there's been a fair amount of interest at recent AAPM meetings on the use of MRI. So this is probably just going to be a review for many of you, but we want to make sure we understand the terminology and the concepts before we get on to more advanced topics. So today I'm going to review the basic physics of magnetism and then talk about the phenomenon of nuclear magnetic resonance. I'm going to discuss transverse and longitudinal relaxation, the T1 and T2 relaxation times. And then I'm going to briefly show and describe some of the MRI systems components and explain how they're used to spatially encode the NMR signal. So first of all, magnetism itself, as you know, is a fundamental property of matter. Magnetic fields are generated by moving charges, and these charges are usually electrons. Typical ways to produce magnetism in normal life are to run an electrical current through a coil like a solenoidal coil shown here on the left, or there are also ferromagnetic materials such as iron in which magnetic fields line up because of magnetic domains, and these bar magnets are commonly used to produce magnetic fields anyway. And magnetism seems to have a kind of mysterious fact. It's very interesting. I got interested in it at a very young age, and I was just thrilled when I got into graduate school to find out that I could produce images with magnets. The magnetic fields are very common. The Earth has its own magnetic field. The strength of the Earth's magnetic field is about 5 Gauss. 5 Gauss is 0.05 millitesla, Tesla being the System International unit of magnetic field strength. And so the relationship between Tesla and Gauss is 1 Tesla equals 10,000 Gauss. So the 1 Tesla is 20,000 times the strength of the Earth's magnetic field. So a collective movement of charged objects is called a current, as you know. And when current moves, magnetic field lines extend away from the path of the current in a perpendicular direction. Unlike electrical charges, electricity, which is produced by charges positive and negative, magnetic fields have a different property called polarity. Polarity is typically called north or south, and it's determined by the direction of the source of current flow. So if you change the current flow direction, you're going to change the polarity of the magnet. There are no such thing, as far as we know, as magnetic monopoles, such as the charges we see. You have to have moving charges to produce a magnetic field. So these moving charges produce a magnetic field, and the magnetic field is characterized typically by magnetic moment. You can see that's a vector here that's extending from north to south. And when you put a current loop that's producing a magnetic field and an external magnetic field, the magnetic field produced by the current loop will tend to align with the external magnetic field. It will experience a torque, and the north pole of the magnetic field produced by the current loop will tend to align with the south pole of the applied magnetic field. And as I mentioned, the magnetic moment, or more specifically, the magnetic dipole moment, is the sort of single easiest parameter used to characterize the magnetic field. It indicates how strong the torque that the magnetic field and the current loop experience and how quickly they'll align. In general, objects try to align with central forces. In the case of a top spinning in a gravitational field, the top, if it's not spinning, will just fall. And the same thing with a magnet. If it doesn't spin, it will just align with the main magnetic field. But the property of spinning, rotating about its axis, changes the physics a little bit. And so when a top is spinning in a gravitational field, it will tend to precess about the magnetic field. And the same for a gyroscope and other objects in relation to gravity. A spinning magnet will tend to precess about the main magnetic field. So on average, its position will be aligned so that the north pole of the magnet will be aligned with the south pole of the applied magnetic field, but it'll be rotating about this. And this produces, in tops at least, the kind of wobble you see when the top slows down. When the top is spinning very quickly, it's almost exactly aligned with the magnetic field. The amount of wobble is very tiny. And the same is true for a magnet that is spinning rapidly in an applied magnetic field. Most of the materials we deal with and put into the magnet, and this includes our patients, have magnetic properties of their own. Magnetic properties of materials characterized by a parameter called susceptibility, and it characterizes the extent to which a material becomes magnetized when it's placed in the magnetic field. One example of a magnetic material is diamagnetic materials, and these are materials that when placed into a magnetic field, the magnetic field inside the material will be slightly less than that of the applied magnetic field. Examples of materials that are diamagnetic include calcium, water, and in fact, most organic materials and most living cells are diamagnetic. Paramagnetic materials have positive susceptibility, so a magnetic field inside paramagnetic materials will be amplified slightly when placed in an external magnetic field. And that doesn't mean they have magnetism or self-magnetism on their own. This only happens when a large applied field is there inside it, as in the case when you stick something in the MRI magnet. Example of paramagnetic materials include oxygen, deoxyhemoglobin, because it has oxygen, and gadolinium-based contrast agents, which use their paramagnetic properties to enhance the MRI images. Now, nuclei exhibit magnetism too. As you know, nuclei are composed of neutrons and protons, collectively called nucleons, and they can be considered to be inside energy levels inside the nucleus, similar to the way electrons are classified as being in energy levels in atomic shells. Nucleons have permitted energy levels, analogous to the atomic levels, and the lowest energy levels in the nuclei are the most stable ones. As you probably already know, transitions from higher energy levels to lower energy levels in the nuclei produce energy, and this energy is released as an emission of a gamma ray photon, very similar to the way visible light and X-ray photons are emitted from atomic transitions. Some nuclei have magnetic dipole moments. To have a non-zero magnetic dipole moment, the nucleus must have number of protons and or the number of neutrons be odd. That is, you have unpaired protons or unpaired neutrons. If the number of nucleons, either protons or neutrons, are even, those spins will pair up just like the electron spins pair up in the orbitals. A quantity of magnetism in nuclei and in electrons are given special units called the Bohr magneton and the nuclear magneton. The Bohr magneton is the magnetic dipole moment for K-shell electrons, while the nuclear magnetic dipole is the magnetic dipole calculated for a proton. Now, it's important that only those nuclei that have finite magnetic dipole moments can produce the phenomenon known as nuclear magnetic resonance. And the phenomenon is a very specific one. In tissue, we have hydrogen atoms in water and fat that are essentially in a liquid state, or at least a fluid state, and are randomly oriented and won't produce any observable magnetization. But when they're placed in a magnetic field, the nuclei align in parallel and anti-parallel directions at two discrete energy levels. And this alignment causes the energy difference, which is the potential energy from which nuclear magnetic resonance is produced. Now, I said before water was diamagnetic. So how do water protons produce NMR? The diamagnetic properties of water are due to their electron magnetic moments, not their nuclear magnetic moments. NMR depends on the nuclei, while the bulk magnetism depends on the electrons. So you place a, say, sample of water in a magnetic field, and there's going to be an energy difference due to a difference in the number of proton magnetic moments being aligned or with or against the applied magnetic field. And the larger the magnetic field, the greater this difference is going to be, and therefore the greater the energy difference is going to be between the two states. So you go from 0.5 to 1 Tesla to 1.5 Tesla. The energy difference between the two nuclear states increases proportionally. This can be characterized to a degree by what is known as the Lamarr equation, which relates the frequency of magnetic resonance, which is related to the energy difference between those states, to the applied magnetic field strength. The constant of proportionality that relates these two quantities is the gyromagnetic ratio, which is, has units of radians per second per Tesla. Gyromagnetic ratio is a characteristic of each individual nucleus, and therefore each nucleus will resonate at a specific resonant frequency called the Lamarr frequency. Now, when you have billions of hydrogen nuclei aligned with a magnetic field, they will precess. The sum of their magnetic moments, or net nuclear magnetization, will precess around that magnetic field, as we talked about before, similar to a top. And this precession is very important because we'll see it involves how the signal is generated. To really describe this, we need to try to come up with a more simplified point of view. Because if we're just looking at the magnetic moment of say, all the water nuclei within a single voxel within a patient, it's going to be precessing at the Lamarr frequency, which is many megahertz per second, or many megahertz, millions of cycles per second. And it's difficult to separate that precession motion from other types of motion. This is analogous to trying to figure out what's going on a merry-go-round as you're standing in the park watching the merry-go-round go around and the horses go up and down and the people walk around on it. But if you get in what's called the rotating frame, analogous to actually being on the merry-go-round. You can see the horses go down, you can see the people walking around. It's much easier to discern their motion than it is when you're observing it standing outside of the merry-go-round. And so that's what the rotating frame actually does. It actually gets rid of the motion due to precession of the magnetization about the main magnetic field. And now we just look at the vector and the motion that occurs within the rotating frame. And so we can generate an NMR signal by applying an excitation magnetic field. So this is a second magnetic field that's applied perpendicular to the main magnetic field produced by the big magnet. This flips or nutates the magnetization from being aligned with the main field into the transverse plane. The transverse plane here is called the X prime, Y prime plane. The primes denote that we're in the rotating frame. So we're looking at the magnetization flip in the transverse plane. And the component of the magnetization in the transverse plane is what produces the NMR signal that we can receive. And so it's going to be precessing still, even though it's in the transverse plane, at the resonant frequency. And we're going to be able to pick up a signal at that resonant frequency in our receiver coil, and it'll produce a signal, decaying signal called a free induction decay, or FID. This signal decays with a time constant called T2 star. And we'll explain what that is in a second. But it's mainly due to the reason that the signal decays is due to dephasing of the spins. They all start out in what we call coherent state, but then due to microscopic and macroscopic processes, there's dephasing of the signal across the sample, and the signal goes away. So I've already demonstrated, but I haven't really explained, the net nuclear magnetization is the sum of all the magnetic dipole moments of all the nuclei, and it's described in two parts. The longitudinal magnetization is what is established by the imposing the large B0 magnetic field. That's can range from 0.35 Tesla up to 3 Tesla clinically. The transverse magnetization is what's produced by applying a much weaker B1 magnetic field perpendicular to the main field, which flips the net nuclear magnetization from the z-axis towards the XY plane. And it's the component of the magnetization in the XY plane that actually produces the NMR signal. After you turn off the RF pulse, you'll get the signal for a little while, but after a while there'll be dephasing, as we've already talked about, but there'll still be magnetization in the transverse plane. But slowly the magnetization will shrink. This purple vector, MXY, will shrink while the red MZ vector will increase again, and it'll get back to a state of equilibrium. So the flip angles allow us to select how much of that Z magnetization we want to rotate into the XY plane. It works by the principle of torque, which we talked about before, and the rate of rotation occurs based on the Lamar equation also, but now it's the Lamar equation with B1 in here. So this rate of rotation has a characteristic frequency which depends on the gyromagnetic ratio of the nucleus we're looking at and the magnitude of the B1 field, radio frequency B1 field, which is applied, in this case, in the X prime direction, and just sits there because we're in the rotating frame. The flip angle is determined by adjusting either the strength of the B1 field or the duration it is on, the T here. And so you can calibrate your flip angles based on the amplitude of your B1 field and duration. You can decide whether you want a small flip angle and only have a small amount of the transverse magnetization, or a large flip angle where almost all of your net magnetization is in the transverse plane. And this is useful for different types of pulse sequences. So that's your basic physics of NMR. Before we start talking about MRI, I've got a few questions. I got a question here. So what is the processional frequency, that is the resonant frequency of hydrogen 1 nuclei at 0.5 Tesla? And if I tell you that the reduced gyromagnetic ratio, that is 42.58 megahertz per Tesla, what do you think frequency you would resonate at 0.5 Tesla?
All right, great. Thank you so much for introducing that question. So for those of you who have been doing these webinars, you know that these poll questions are available on the sidebar. You can go ahead and weigh in. And Jeff, it looks like most everyone has selected an answer.
Yeah, and it looks like they're mostly right, too. So the correct answer, as most of you said, is 21 megahertz. Now, these other answers are the answers for other commonly used clinical MRI scanners, ranging from 0.35 Tesla, which is 15 megahertz, up to 3 Tesla, which is 126 megahertz. So you can see the resonant frequency is not only a function of the nucleus, but it's also a function of the applied magnetic field. Now I want to move to talking about properties of MRI, the image quality properties, and the most important one is contrast. The reason MRI is so useful is because soft tissue contrast is very high, and not only that, it's very easy to manipulate soft tissue contrast. So with different MRI imaging techniques, you can make contrast, certain tissues stand out more, certain types of cells stand out more. Fundamentally, contrast is modulated by the number of protons in a given tissue, the proton density, we call that. But there are two other important parameters called the relaxation times I've already alluded to, called the T1 relaxation time, which is a function of how long it takes for the magnetization to realign with the main field, and T2 relaxation time, which characterizes the dephasing of the transverse magnetization and how quickly the signal goes away. Other things that affect contrast are bulk motion and water diffusion. They're beyond the scope of today's talk, but hopefully we'll get to them in the future. Now, transverse decay, as we talked about, you apply the radio frequency pulse and you get a signal back. This is analogous to striking a piano key and you hear the signal or the note as the hammer hits the string in the piano. And if you have the sustain pedal on especially, it'll slowly decay. And that's what we're talking about when we talk about transverse decay. The MRI signal is at anywhere, as we talked about, from 15 up to 128 megahertz. So it's not within an audio range, but it decays in the same way. And it's mainly as the signal from the piano string decaying is due to frictional elements in the string, causing its resonant properties to not be able to support this sound. The dephasing of the magnetic spins, or at least the transverse components of the magnetic spins, similarly, you can think of it as being the friction that causes the MRI signal to go away. So we're in the rotating frame. We have equilibrium magnetization established in the main field. We give a 90-degree RF pulse, and all the magnetization is aligned in a coherent manner in the transverse plane, producing a large signal, but then it starts to dephase, and at some point it gets totally dephased. So that's what's happening in the rotating frame. In the laboratory frame, we gave the 90-degree pulse. We picked up a signal, and the signal's decaying over time as the spins dephase. And so that's characterized mainly by what we call the T2 relaxation constant. And the important thing for MRI is that different tissues have different T2 values. And so that the signal from water decays more slowly or dephases more slowly than fat or solid tissue. And therefore, we can to some degree, differentiate these tissues based on their T2 relaxation properties. Now, nothing is as simple as that in real life, and actually, there are more things going on to cause dephasing than just the T2 processes, which are microscopic interactions of the water atoms we're looking at with other types of molecules in the tissue, such as proteins. The other things that can be happening are the susceptibility effects. I already talked about susceptibility of materials, and you know that most living tissue is diamagnetic. It can also be various other things in the body, in the tissue, which cause local magnetic inhomogeneities, and they will actually accelerate this dephasing process. And so instead of the signal decaying as T2, it'll decay as what we call T2 star. So T2 includes the T2, but there's other processes involved. So T2 star is always shorter than T2. The other major contrast mechanism is called T1, or longitudinal relaxation. It describes the growth of the net magnetization as it relaxes from being in the transverse plane towards reestablishing itself longitudinally, aligned with the B0 magnetic field, which defines the z-axis. T1 is the time needed for recovery of 63% of the magnetization after a 90-degree pulse. As you can see, it's in this exponential equation here, which shows that it's a recovery thing. That's where the 63% comes from in here. And you don't get full recovery until you're up to 4 or 5 times T1. That's when you're getting close to this value here, the exponential t to the negative T1 being 0. So this is a graphic display of how T1 works. You have recovery of the magnetic field. There, it goes in that direction. And then it goes back up. So after a 90-degree pulse happens, it goes down, but then it comes back up. And so what we see is we have the spins aligned. They're all precessing, and they're tightly precessing about the main magnetic field here because of the application of the large B0 magnetic field. But then you give a 90-degree pulse, and the Z magnetization goes away, and it all goes into the transverse plane. But then it slowly recovers until it's back to its original value. And so you can think of the Z magnetization as being a reservoir of spins with high potential energy that you can exploit to produce the MRI signal. And like the T1, like the T2 of tissues, the T1 of tissues are different for different tissues. On the extremes are water, which has a very long T1, and fat that has a very short T1, and other tissues are in between those. The fat having a short T1 means it doesn't take very long for the magnetization that's in the transverse plane to recover to be fully longitudinal, and you can excite it again quite rapidly and get a high signal, whereas the long T1 of water means that you have to wait quite some time if you want to get the full signal from water after you've gotten the initial signal, because it takes very long to reestablish itself. And so I mentioned the different tissues have different T1s and T2s. Here are some examples you can see. One of the nice things people learned out early with MRI was you could differentiate gray matter from white matter, and that's essentially due to their T1s being different. As I mentioned, cerebral spinal fluid has a very long, because it's mostly water, has a very long T1. Fat, on the other hand, has a very short T1. Notice also the T1s tend to be hundreds of milliseconds to seconds in duration, whereas the T2s tend to be tens of milliseconds in duration, maybe up to a little over 100 milliseconds. And so that means that these relaxation processes have different time scales. And that gives them a degree of separability that we can use to manipulate contrast on the basis of T1 and T2 somewhat independently. We call it T1 and T2 weighting. And so you have this recovery process with T1, so it goes in a different direction than the decay process with T2, but they're also on different time scales. So here's my second question. Let's see if you can figure this out. Regarding NMR relaxation times, which is true? T1 characterizes a decay process, T2 characterizes a recovery process. T1 is usually longer than T2, or T2 star is usually longer than T2. And you guys are good.
All right, if you haven't had a chance to weigh in on this poll, please go ahead and take a moment to answer the poll question. All right, Jeff, looks like most people are getting the right answer, I think.
Yeah, I think so.
Okay, I think we can go ahead and review the answer.
Okay. So, correct answer is C. T1 is usually longer than T2. T2 cannot be longer than T1. T2 can only be as long as T1. It's physically impossible for T2 to be longer than T1. In very, very pure water, T1 is equal to T2. Typically, T1 characterizes a recovery process, not a decay process, and T2 characterizes a decay process and not a recovery process. And T2 star is always shorter than T2 because T2 is included in T2 star and other factors enhance this decay process. Okay, now I want to talk a little bit about hardware. Main piece of hardware, the most expensive piece of hardware, and the one that MRI systems are characterized by is the main magnet that produces the big B0 magnetic field. There are 4 different types of magnets that are used for clinical MRI: permanent magnets, air core resistant magnets, iron core resistant magnets, and superconducting magnets. Superconducting magnets have become the most dominant kind because you can produce higher magnetic field strengths. They're much more homogeneous, and they use less power. And so I'm going to concentrate what little I say about magnets on those. But just to explain, air core resistant magnets were the first generation. They consist of large coils wound in copper wire or aluminum bands, and electric current was passed through them to generate the magnetic field strengths that range from about 0.2 to 0.3 Tesla. Superconducting magnets are similar, except the coils are immersed in a liquid cryogen, typically liquid helium. And the coils are made of a special type of metal that can become superconducting at very low temperatures. And so all you have to do is hook a current source up to them, turn on a heater so you have a little bit of resistance, apply current to the superconducting magnetic coil, turn off the heater so this cools off and the resistance goes away. And then the current will circulate perpetually in the superconducting magnet, and it'll slowly decay because of imperfections in the windings and in the connections, but you only have to recharge it once every 2 to 5 years. And it'll produce a very strong magnetic field. Pretty much all the magnets greater than 1 Tesla are superconducting magnets now. This shows a cross-section of a superconducting magnet. You have the main coils that are characterized here. This is in cross-section, so this is just splitting the magnet down the middle, taking a look at all the coils that are in it. The main coils are here. In this one, there's 6 main coils. Different size represents different current densities. There are also active shim coils in here, which are electrical shims used to homogenize the main magnetic field. There are switches. You put the main leads down on the top here, and all this is submersed in liquid helium, which keeps it close to absolute zero so that the coils remain superconducting. And there's a recondensing or circulation system, and the liquid helium boils off. It will go out, and it will be recompressed and then reinserted into the magnet. And that's why you can go several years. You can go a couple of years without having to add any extra helium. So if you look at this other cross section across the end, you have your superconducting magnets, coils in the middle, immersed in liquid helium with shim coils. Then inside the bore of the magnet, you have the open bore of the magnet, you have the gradient coils and the RF coils. Now this is what the magnet looks like. The key parameters, in addition to the field strength, the stability, which superconducting magnets are extremely stable, and then also magnetic field homogeneity, which means you want the magnetic field strength to be essentially perfectly uniform across the entire part of the body that you're imaging. This is what a magnet looks like with its covers off. The field strengths of these superconducting magnets range from 0.3 to 7 Tesla. All the ones over about 1 Tesla are going to be superconducting. These magnets are always on. In order to work and repair the magnet, if something's wrong with it, you have to discharge the magnet using your power supply and taking the current out of the magnet. The second major component next to the magnet is the radio frequency subsystem. It includes the coils which are used to transmit the excitation RF pulse and put energy into the spin system, and also the coils that receive the signal from the spins. Some coils are designed to do both these functions. Some coils just transmit or just receive. Once the coil is received, the signal is digitized using analog digital converter for processing. And a lot of the difference between different systems and their sensitivity of them to produce the MRI signal depends on RF coil design. So RF coil design and associated RF electronics are some of the most important trade secrets of the various MRI companies. But there's similarities, and the radio frequency coils, the older ones were what we call birdcage type coils. Put the knee and the arm in those. You still see a lot of these around. The newer, you also have surface coils, which are smaller coils that are used to get there. You can receive more signal from them if you're imaging smaller parts. So they can be put close to the part of the body you're interested in getting in imaging, and also it doesn't detect noise from other parts of the body, because the major source of noise in an MRI study is the patient themselves. But more recent MRI systems use phased array coils that combine the signals from multiple surface coils. So there's one there and one there and one there. And they're worked together in what's called this phased array, and that's where the radio frequency technology has been going recently. Now, the processing of the NMR signal is similar to the processing you do in your head when you're listening to music. This is one note from a Bach prelude. It's this note right here, but you don't see this. You hear a note. It just sounds like a specific frequency to you, even though it's really a decaying signal with time. And that's generally what happens with MRI. You have a signal decaying in time. It's processed, and the MRI system isn't processed by a brain. Well, I guess it's a kind of brain, but it's a Fourier transform algorithm that converts the signal from being a time domain signal to being a frequency domain signal. And so you can separate signals from different frequencies, and NMR was first used to separate signals that had different chemical signatures. So here's the free induction decay signal, has the very strong beat pattern. It's really two frequencies beating up against each other. And you do the Fourier transform and you see it's mostly signals from fat, but there's also some signal from water. And this is from butter, actually. So when we think about localizing the signal, unlike X-rays, where we have photons we're trying to image that are very particulate and almost like bullets, and we can shoot them through a patient and see which ones get stuck in the patients and which ones get through and produce shadowgrams. We can't do that in MRI because even though we're producing electromagnetic photons, they have much larger wavelengths on the order of a meter. And so you can't localize precisely with that large a wavelength. So what you can do is kind of think about what characteristics electromagnetic waves, and in fact all waves have, and it comes down to three. You have amplitude, you have frequency, and you have phase. So the strategy for MR signal localization is to take advantage of those three properties of electromagnetic waves. And this is done using gradient coils. Gradient coils, as I showed you previously, are inside the bore of the magnet. They're designed to change the main magnetic field so that spins at different locations precesses slightly different frequencies. And their frequency is directly related to their location. Typically, in MRI pulse sequences, gradient coils are turned on and off in short bursts on the order of 10 milliseconds or less. And from this, this encodes the spatial information into the NMR signal and allows us to construct our 2 or 3D images using the same Fourier transform that I just showed you. So there are three gradient fields. There's X and Y and Z. We can think of the X as being the sagittal plane and the Y being coronal and the Z being producing the axial plane. The important thing, these gradient fields are linear, at least over the range of the body part we're trying to image. We want them to be very linear so that the magnetic field changes they produce are directly related to the spatial position within the magnet. And the image data, which required and looks something like this display on the left, we call this the raw data. You do a two-dimensional Fourier transform and you get an image like this. Now this is the encoded data and this is the decoded data. So the Fourier transform is decoding the data and turning it temporal changes in the NMR signal into images. So how does that happen? Well, first of all, if the magnetic field were homogeneous, then all the protons in the body would spin at the same Lamar frequency. And when an RF signal is applied, the entire body will return a single signal. So the gradient coils are used, and here they are in the magnet. There's the body RF coil that can transmit and receive, transmit the RF pulse and receive an NMR signal. But here are the gradient coils. They're all together in that case. And then there's a shield also, gradient shield. And this is the magnet power supply, which is only turned on when you're ramping up or ramping down the magnet. Here the radio frequency power supply, control boards for the control part of the MRI system. Here's the gradient power supplies. There's three gradient power supplies, one for each gradient coil. So you superimpose these linear gradient fields, and they create position-dependent variations in the precessional frequency of the protons, changing the NMR signal. And so you can either do this while you're doing the excitation pulse, or you can do it while you're collecting the MRI signal, and it's different. So let's talk about just for clarity. We're going to say that the slice select direction is in the Z direction, so that's aligned with the main magnetic field in the magnet, so it's along the bore of a superconducting magnet. The X is the frequency encoding, say that's across the magnet, or across right to left on the patient if they're lying on the table. And the Y is the phase encoding, which is anterior, posterior, as the patient's lying on the table or floor to ceiling. Now, it doesn't have to be this way. These magnetic fields will can be manipulated so you can have slice selection, frequency, and phase encoding in any oblique plane, but this is just for simplification. And these are the geometrical arrangements of the gradient coils in the magnets. And look at the bottom left here, you see the z-axis is basically two coils with opposed currents in them. So they cancel out in the middle right between them. And the magnetic field increases in one direction away from the center, or what we call the isocenter of the magnet, and decreases in the other direction. The X and Y gradient coils are somewhat different. They're four saddle-shaped coils, but they have the same effect. There's no great effect of the gradient field in the middle of the magnet, in the isocenter, but as you move away from isocenter, the coils increase the magnetic field in one direction and they decrease it in the other. The X and the Y's are very similar to each other. They're just basically rotated 90 degrees. So as I said, the gradients have the effect of changing the magnetic field. Without the gradients, you have a constant magnetic field. You get the same signal no matter what position you're talking about in the patient. But when you change the magnetic field, that's going to change the resonant frequency. So you get a lower signal, lower frequency signal in one part of the body than you do in another part of the body. So the first thing we manipulate is the amplitude of the NMR signal. We do this through a process called slice selection. Slice selection occurs because you apply your magnetic field gradient, your slice select gradient, at the same time you apply your radio frequency pulse. And when you do this, you limit the range of excitation by depending on how strong your slice select gradient is. And so this equation down on the left shows the resonant frequency equals gyromagnetic ratio times the magnetic field strength times the plus the z position times the gradient strength. So you can vary the position of your signal by varying the applied resonant frequency. So if you want to change the slice thickness, you're applying, in this case, the same RF excitation with the same RF excitation bandwidth. But if your gradient's very strong, you get a narrow slice. If your gradient is relatively weak, you get a thicker slice. Similarly, you can change the position of the slice by just changing the center frequency, even though the pulses have the same bandwidth. And here's your Z gradient. So slice 1 is at this position, slice 2 is at that position. Slice 3 is over on the right here. So that's how you manipulate the slice selection and ensure you only get signal from a thin region within the patient. So that gets you a slice, but how do you create an image from the signal you get from that slice? Well, the next strategy is called frequency encoding. It's also called your frequency encoding gradient. It's also called your readout gradient, and that's because it occurs during signal reception. It has to be on during signal digitization. And so this is going on while the slice select gradient's already been turned off, and it's encoding the signal. It's changing the frequency of the signal going across the patient from left to right here. And so there's different frequencies coming from the right arm than there is from the left arm. And so you can sort where the signal's coming from in that direction by the frequency. And so at lower frequencies, you get a lower signal. At higher frequencies, you get a higher signal. And you calibrate the gradient to the receiver bandwidth, which is related to how fast you digitize the signal, and the field of view that you want for your image. So the field of view is going to be related, constant proportionality, gyromagnetic ratio, but the field of view is going to be proportional to the receiver bandwidth divided by the frequency or readout gradient, frequency encoding or readout gradient. So as the bandwidth, receiver bandwidth is increased, the field of view will increase, or as the strength of the frequency encoding gradient goes down, the field of view will increase. The third process is phase encoding. It requires a little more explanation. Phase encoding goes on between RF excitation, after you've given the radio frequency excitation pulse, but before you acquire the data or digitize it. And phase encoding is also different because you only get to phase encode one signal at a time. And this phase encoding is the main reason that MRI takes a relatively long period of time. The amount of time taken to frequency encode and slice select together are only a few milliseconds, but phase encoding can take hundreds of milliseconds to minutes. Now, by phase encoding, I mean we're changing the relative phase of the signal you get from the NMR spins. You turn the gradient on briefly, in this case in the AP direction, and then it's turned off. While the gradient is on, the nuclear spins have different resonant frequencies, which are dependent on their position in the patient. But when the gradients turn off, they go back to their original resonant frequencies, and now all they're left with is phase changes. This is analogous to time zone changes you see in clocks that come from different places around the world. Like clocks, different zones have different phases, but they're still at the same frequency, 1 day per 24 hours. And so your phase encoding gradient changes the phase as a function of position in the AP direction in the patient. And once the gradient's turned off, all the protons will be in the same main magnetic field again, but they'll have a phase shift that will last until you do the readout or data acquisition. Phase encoding gradient cannot be on during the RF pulses, and a separate echo signal is needed for each phase encoding step. So you acquire the data with a slice select and frequency encoding and one phase encoding step, but then you have to repeat that with a different phase encoding each time. This is done by changing the strength of the phase encoding gradient for each successive acquisition. Okay, so let's have another question here. Which of the following defines the volume of tissue from which MRI signal originates? The main magnet, the surface coil, the slice select gradient, the frequency encode gradient, or the phase encoding gradient?
All right, everyone, this is our last question, so be sure to go ahead and weigh in. All right, Jeff, it looks like a lot of folks are weighing in. I think we can go ahead and review the answer.
Okay, seems to be a little confusion on this one. Okay, so let's go over this. The correct answer is it's the slice select gradient. That defines the volume of tissue from which the signal originates. That's the amplitude encoding. The main magnet energizes the spin system, but it's designed to be very homogeneous and no changes across the volume from which we do the imaging. Surface coil is a type of radio frequency coil that receives the NMR signal, and the frequency encoding gradients give us X position in this case and phase encoding Y position, but it's a slice select gradient through the amplitude encoding process that defines the volume of tissue. It works along with the radio frequency excitation pulse in order to together define the location and the thickness of the tissue, that the slice of tissue that we look at. I want to wind down here just talking a little bit. I mentioned pulse sequences before, and I've alluded to how these gradients and RF pulses have to be turned on in a specific order in a specific manner. And this is defined by our pulse sequence diagram here. It typically has 5 lines: radio frequency excitation line, which shows the radio frequency pulses, and then a line for each of the gradients we use, and then the signal reception line at the bottom. So at the top, you have a radio frequency pulse, and you'll note that at the bottom of the diagram, right below the radio frequency pulse, it says that t equals 0. So we need to define a time equals 0 so we can define the phase of the NMR signal. If we don't set that some time equal to 0, because phase is a relative thing. It only goes from 0 to 360 degrees. We apply the slice select gradient during the radio frequency pulse. We also have this rephasing component here, which is designed to eliminate any phase changes that go on during RF excitation. This is because we want all the phase changes to be due only to the phase encoding gradient. Similarly, on the 4th line where we have frequency coding, we have a negative frequency encoding gradient, which is designed to anticipate dephasing due to the frequency encoding gradient, so there will be no phase changes due to the frequency encoding gradient at the time that we collect this, in this case, a gradient echo signal or a refocused free induction decay signal. You'll notice here's the frequency encoding gradient, and here's the phase encoding gradient. And the phase encoding gradient is represented somewhat differently from the frequency encoding gradient, the slice select gradient. And that's because it's incremented each successive acquisition. So if you're going to acquire, say, an image that's 256 by 256 matrix pixels, then you're going to acquire 256 frequency encoding data points on each excitation, but you have to acquire 256 separate excitations in order to get all your different 256 phase encodings going. So to summarize, hydrogen is the nucleus of choice for MRI studies. Most typically, we try to image the hydrogen in the water molecule. But materials in general and tissues in specific have magnetic properties that will cause the magnetic field, the applied magnetic field, to shift inside of them. Most tissues are diamagnetic, which means that the magnetic field strength inside the tissues are slightly less than the applied magnetic field strength. Other substances, such as contrast agents, can be paramagnetic, where the magnetic field strength increases above what the applied magnetic field. The NMR signal comes from the magnetization set up by the main magnetic field, but in equilibrium, it's in longitudinal, that it's all aligned with the z-axis or the B0 magnetic field, and we have to apply radio frequency energy to create transverse magnetization, which produces the NMR signal. Once the NMR signal is produced, it will decay with a characteristic time constant called T2 relaxation, and will stay in the transverse plane until it slowly realigns along the z-axis through the process of T1 recovery. To produce images, we encode the signal using gradient coils that change the magnetic field in each of the 3 orthogonal directions. The slice select gradient works with a radio frequency excitation pulse to define a slice from which the signal is produced. The phase encoding gradient creates rows with different phases, while the readout or frequency encoding gradient creates columns with different frequencies. By being able to differentiate the phases and frequencies through our Fourier transform, we'll be able to create an image in which each voxel has a unique combination of phase and frequency. And the amount of protons in each voxel determines the strength of the received signal. But we've only touched on how the signal is decoding. And that will be a topic for a future discussion. In the meantime, there is a book available. There's several good books available. This is one that I contributed to. And if you'd like to learn more about it, I invite you to read it. Thank you very much for your attention.
Thank you for presenting the webinar, Jeff, and thank you all for joining us for this free event hosted by WePass. I just want to remind everyone to be sure to register for the next WePass webinar on MR guidance in radiation therapy presented by Dr. Catherine Mittauer, staff medical physicist at University of Wisconsin-Madison, and that'll be on Wednesday, January 17th, 2018 at 5 p.m. Eastern Standard Time. And just as a reminder, this and other recorded webinars will be available to WePass subscribers. You can register through wepass.com to become a subscriber. For up-to-date information about upcoming webinars, be sure to follow WePass on Facebook, Twitter, and Google+. Thanks again, Jeff.
You're welcome. Thank you for inviting me to do this.